Okay. Okay, so we were at example 5.2.4. Okay, or we stopped just before that. Alright. Okay, so example 5.2.4. Okay, you were asked to find the reciprocal of z equals 2 minus 3i. Okay, you were asked to find the reciprocal of z equals to 2 minus 3i. So if you recall from one of the first few examples, what we did is we multiplied the denominator. Okay, maybe let me just write in pen. Okay, so what I taught you all was to multiply this so-called fraction, by this number, 2 plus 3i over 2 plus 3i. Right? Okay, so now you can actually see that if I treat this as z, then this is essentially z conjugate. Okay, so what you previously learned about this skill, realizing the denominator, now that you have learned conjugates, right, it's just, to multiply the denominator by its conjugate. Okay, and why does that help? That helps because you learn this result. Z times Z conjugate equals to the modulus of Z squared. Okay, which I highlighted to you as one of the most important results in this chapter. Okay, although strangely, sometimes I highlight already, I go to class, clearly all my students forget. Something like this. The last time I mentioned in the topic of vectors, A dot A is magnitude of A squared. I highlighted this as an important result in the chapter of vectors 1. I go into tutorial, everyone don't know that this was a highlighted result. Okay, so if I say it's a highlighted result, make sure you highlight and you store it in your brain. Alright. Okay, so let's go on. Okay, so the steps are just another way of doing this lah. Okay, what is shown here. Alright. Okay. Okay, so quick check. Okay, is it necessarily true that the non-real roots of any polynomial must occur in conjugate pairs? True or false? If you're already rusty, turn back to your previous few pages on this section. Okay, conjugate root theorem. Tell me whether this statement is true or false. What do you think? You read? Oh, ask. CNY 太久. Eat too many pineapple tarts, then all forget everything already, right? True or false? Okay, so let's go back to what does conjugate root theorem say. What does conjugate root theorem say? Read the statement to yourself. Okay, I will not repeat what's in the notes. Then you compare to this statement, you tell me whether this statement is true or false. True or false? The answer is false. Why? What is it that I'm missing? I did not mention that the coefficients are real or not. I didn't say, right? So in general, this is false. Okay? Can I? Okay, so next. The roots of any polynomial with real coefficients must occur in conjugate pairs. True or false? False. Give me a counter example. I thought conjugate root theorem say they must occur in conjugate pairs. True or false? Yes, but if the roots are already real, so for example, something like this. Okay, in its factorized form, this is a quadratic polynomial, right? Okay, are the coefficients of this quadratic polynomial after expanding going to be real or not? Yes. Do the roots occur in conjugate pairs? No. Okay, so if the roots are already real, you may not see conjugate pairs. Alright, so I'm using these true and false questions, okay, to highlight certain subtle points of the conjugate root theorem, which a lot of people tend to miss out. Okay, so please make sure you pay attention to that. Okay, next. The moduli of a conjugate pair are equal. Meaning to say, this and this are equal. True or false? True or false? How do the conjugate pair appear geometrically in the Argand diagram? They are what? Turn back to your relevant page. They are reflection of each other about the real axis, right? So what does it mean by modulus? Modulus is the distance from the origin to the point representing a complex number, right? So are they going to be the same? Yes. Okay, so this is true. Statement 3 is true. Okay, statement 2 is false. Okay, next. The argument of negative z is equals to the negative of argument z. True or false? Look at your diagram. You already have a preset diagram. You don't even need to sketch again. True or false? If your point representing z okay, was here. Okay, so let's say this was the point representing z. Not today so late. Okay, where would the point representing negative z be? Here, right? Okay, so is the argument the negative of each other? No, okay, so okay, anyway, you can draw yourself and see, right? Clearly, this is not the negative of this one, right? But the argument of which complex number will be the negative of argument of z? The conjugate. Okay, if you drew the conjugate on this diagram as well, okay, you realize that the arguments are negative of each other. Alright, draw it for yourself. Okay, next. Argument of the complex number x plus iy. Okay, I'm going to give you the fact that x and y are real. Okay, so don't tell me what x and y not real, so not true. Okay, so x and y are real. This is a Cartesian form. Okay, so is it true that argument of x plus iy is tangent inverse of y over x? True or false? True or false? You go back to the previous examples. What did I mention about the use of tangent inverse? Can you just use directly? No, you must find the basic angle first, right? Okay, then after that you work out accordingly. So the answer for this is false. So for today's okay, very lag. Okay, 4 falses, 1 true. Alright, okay, so let's go to the next section. I asked you to revise our Maclaurin series, right? Okay. Okay, now, okay, let's quickly go through this. Okay, so just to recall, later we'll need to use this law of indices. Okay, so just to recall, a to the power of xy, right, is a to the power of x bracket whole thing to the power of y. Alright, then you also have another one for a times b whole thing to the power of x. Okay, what are the Maclaurin series for cosine, sine, and e to the power of x? Okay, these are the Maclaurin series. Okay, so later on we'll use some of this series. Okay, now, okay, so this is what you'll be learning for today's lecture. Okay, we're going to try our best to finish all of this. Okay, so now you learn. Okay, so let's go on to the first part. Okay, can you turn to page, before you start to get lost, let me give you a point of reference. Page 14 of your lecture notes. Okay, previously you learned a Cartesian form, right? Okay, now that you have learned modulus and argument, okay, I'm going to introduce you a second form called the polar form. Okay, now, you look at this diagram, you have the modulus and the argument of a complex number. Okay, the point of course represents the complex number itself. Okay, can you tell me, in terms of r and theta, what is x? So let's say z is x plus iy. This is the point representing z. Okay, what is x in terms of r and theta? What is y in terms of r and theta? Very quickly. You need to use your trigonometry. X is equals to r cosine theta. Okay, thank you. Very good. What is y? R sine theta. Correct? Not difficult, right? Okay, so I can actually write z as this. Okay, and this is what I call the polar form of a complex number. Okay, this is what I call the polar form. It is actually more or less the same as the Cartesian form, just that I rewrite it in terms of r cosine theta plus I sine theta. Okay, where you can see the modulus and argument. Okay, now